Anybody left at all? Thank you. Thank you. Thank you. All right, time's up. Anybody left for the quiz? Last person? Anybody else over than here? Okay, it's going to get too busy. All right. Okay. So this was all about quiz number 5. If you have a question about it, please hold on until next session on Thursday, because we have distance students who have not taken the quiz yet. A few announcements. I believe your final exam is on the 12th of May, which is I think 4 weeks from today. I believe. I'm not sure. Ironically, they have put the exam at 7:30 a.m. So first thing that I have to do is I have to return all of your graded homework assignments and quizzes, so you would decide if you want to take the final exam or not. Because if you have done well, if you look at the syllabus, if you're doing well in the quizzes and homework assignments, you don't really have to take the final exam. I think that's all in terms of announcements. I also have a kind of a handout. It's 3 pages. Just make sure this doesn't get mixed with the returning homework assignments. All right, so we are going to continue our discussion and hopefully wrap up our discussion on multi-level power electronic converters. As we have seen so far, there are 3 main categories for these converters. The first one that we studied was cascaded H-bridge converters. The second category was diode clamp converters. And finally, the last one was flying capacitor converters. They all have advantages and disadvantages. For instance, if you want to compare a flying capacitor versus a diode clamp converter, the flying capacitor converter needs less number of switches, which is good, but at the same time, if you're looking at the 3-phase application, you need a lot more capacitors because each phase needs its own independent capacitors. Whereas the diode clamp converter, in addition to the switches, you also have diodes, but at the same time, the capacitors that you use could be used for a 3-phase application, the same capacitors for all 3 phases. So that's actually going to make your system a little bit simpler. Most of the times, these capacitors are used as an inverter or a rectifier, which is the opposite of an inverter, which basically processing AC power on one end and DC power on the other end. And I'm not going to cover those applications because they're kind of obvious, and there's a lot of paper out there actually discussing them. So if you're interested, just Google them or look at IEEE Explorer. At the same time, they have some non-classical applications that we kind of started discussing last time, which is, for instance, when you're trying to convert DC power into one DC power to another. For instance, the topology that we looked at last time was this guy over here, which is like a cascaded H-bridge converter. So what you do is from 0.5 to 1, you have the option of doing, for instance, basically 4 different levels, 0, or VDC1 plus VDC2, or VDC1 minus VDC2, or negative VDC1, negative minus VDC2. And then depending on the duty cycle that you're switching at, for switches S1, S2, S3, and S4, you end up with a voltage transfer ratio that is D4 minus D3 times VDC2 plus D2 minus D1 times VDC1. So if you are curious about what is the advantage here is somehow we have been able to kind of combine two sources into one source, and there is a giant category of papers out there which are focusing on multi-port or multi-input DC-DC or converters in general. So this could be an example of a multi-input converter. So technically you have two sources as your input and you have one output. One, for instance, application could be, again, not necessarily this is the best way of doing things. For instance, you have a solar panel and you have another solar panel, or you have an energy storage system like a battery and a solar panel, or you have a fuel cell and a solar panel, and somehow you want to combine them together using only one converter. This could be an option. The second topology that we kind of left kind of unfinished is another application of using a multi-level converter, in this case a flying capacitor converter for a DC to DC application. So on the left-hand side of the topology, I have my main DC source. Then this is a flying capacitor topology. So I have one, for instance, you can have one or multiple capacitors. In this case, the topology is simple, so you only have one capacitor. So it makes sense to regulate the voltage of this capacitor at half of Vin. So the voltage of the cap is regulated at Vin over 2. You have 4 switches. We don't talk about switch realization because it depends on the directionality of what direction the current is flowing. Is it really flowing from left to right or right to left or both? And the switching pattern is, so I'm actually plotting Vx over here, which is the voltage of the left-hand side of the inductor with respect to the ground. So I'm kind of applying like a kind of a buck type kind of a switching scheme over here. First, I apply a positive voltage, but this positive voltage is obtained by turning S2 on and S1 off. So technically I have Vn, and on top of Vn I have the capacitor flipped added to that. So I have Vn minus Vc, or Vn minus Vn over 2, which is ultimately Vn over 2 applied. Then I apply nothing or 0 basically, meaning that the top switches are open, the bottom switches are on. Presumably if the power flow is always from left to right, the bottom switches are just 2 simple diodes. You don't really need switches down there. And then I kind of repeat the same sequence for the remaining half of the switching cycle, but this time I apply just the capacitor by turning S1 on and basically S2 off. So this time only the capacitor is kind of providing power to the load. The inductor on the left-hand side doesn't see the difference. Is it really Vn minus Vc or Vc? Because Vc is half of Vn anyway. But capacitor actually sees the difference. So if you are curious about the charging cycle of this capacitor, so let's pick another color. Let's pick red. And okay. So in this cycle, because assuming that the current is from left to right, or my load is actually a real resistive load and my source is a real source, in this mode, capacitor is getting discharged. I'm sorry, C is charged. And in this mode, capacitor is actually providing power, so it's actually discharged. So one observation is we don't need a bidirectional current to be able to regulate the voltage of this capacitor, or even a positive current would do it. So technically all we got to do is, if our inductor current is symmetric, and it is actually symmetric unless there's a transient going on, just make sure the length of these two modes are almost the same. But at the same time we can have a feedback loop to measure the voltage of the capacitor. Is it really at Vn over 2? Is it a little larger? Is it a little lower than a compensation network? And that would actually kind of tweak the length of this mode, for instance, compared to this mode. Make one of them a little bit longer than the other, so you're adding a little bit of asymmetry in the system to be able to charge or discharge the capacitor voltage. As long as the inductor current is concerned, it's just a classic buck topology. What did I do? So inductor current rises because this is definitely larger than the output voltage, then falls like a freewheeling kind of a thing, then rises again, and then falls, and then does it like this. As long as the control at the voltage transfer ratio is concerned, let's take a look at that. The ratio between V out or V in over 2 and V in over 2, because technically this level is V in over 2, right, is D. And then you can debate how to define D. You can argue that this length could be labeled to be D times half of the switching period. By this definition, your duty cycle could vary from 0 to 1, kind of like what happens in the buck topology. Or you can actually consider this length and then add this length and then divide it by the whole period, and that gives you the same D. So honestly, it doesn't really matter how you define D. So D could be variable between 0 and 1. All right, so the overall voltage transfer ratio would be okay. So if you compare it against the classic buck topology, not only you're kind of stepping down your voltage by the factor of D, also you're stepping down by a factor of 0.5. So in some applications, you would like to have a large, I don't want to call it attenuation, but anyway, a stepping down kind of a extreme step down kind of application. For instance, this is in a rack, for instance, in a server farm. The power that is supplied to this rack is 48 volts. The motherboard needs maybe 2 volts or 3 volts or whatever it is. Using just a classic buck topology to do that would not be very effective, either in terms of efficiency or extreme duty cycles or inductor values and things like that. So either you have to use 2 buck converters cascaded with each other, so each one of them kind of shoulders the load, or use a topology like this, which is directly doing that. Using 2 converters in cascaded may not be the best choice, because then you have 2 inductors, 2 capacitors. It's a 4th order system. Controlling the system may become a problem. Cascading the topologies, we saw that output impedance, input impedance kind of a thing may actually mess up our stability over here. We are still dealing with a 2nd order system. There's only 1 inductor and 1 capacitor. So inherently, this topology has the capability of stepping down the voltage twice as much than the buck converter can do, or half as much than the buck converter can do. So there's an advantage here. Yes?
I have a question. If in some application we want to limit the current also, so how can we do that? Because if in this case the current would be increasing if we decrease the voltage, considering power balance thing.
Okay, so limiting the current to protect the devices, or for what purpose do you want to limit the current? Like a short circuit fault kind of a thing?
Not a fault. If power rating of that is very low.
This doesn't do that. So for instance, so the question is, if you have a low voltage, high current application, and we want to kind of put a bunch of elements in parallel, so each one of them is seeing part of the current, not the entire current, can we use such a device like this? This topology by itself cannot do that. However, The whole concept of putting converters in parallel, or like a multi-phase converter concept, you can use this as one of the cells of a multi-phase converter. You can use like 2 or 3 of them in parallel. In that case, you can actually afford that. But this converter by itself cannot do that, unfortunately. Other bad thing about this converter is, so technically the power that is mainly coming from the source has to go through switch S2 and has to go through switch S1. So both of these switches are seeing the inductor current or part of the inductor current. Therefore, your losses are going to increase. But compared to the cascaded buck topology, it's the same story. If you have 2 buck converters cascaded, again, each one of the switches is actually exposing themselves to the entire portion of the entire current. Any other questions? One other advantage about this topology is the real switching frequency and the effective switching frequency are different. So if you remember, I call this the switching period, which is 1 over f. But if you see, the inductor current is repeating itself. Oops, sorry, that's not T, this is T. The inductor current is repeating itself twice in one of our switching cycles. So kind of there's a little bit of an interleaving going on here as well. So like if you are turning your switches on and off with a 100 kilohertz switching frequency, in other words, in every second you turn your switches on and off 100,000 times, your inductor sees a 200,000 basically switching frequency, or 200 kilohertz. So that's an advantage. That means technically when it comes to designing this system, remember the higher the effective switching frequency is, the smaller the required inductor is. So higher frequency, smaller inductor. So it also has an inherent kind of a doubling the frequency effect kind of a thing. So there are a few papers out there just trying to focus on this topology and using it as a DC to DC converter. So just I can show you, if you are interested, I can find them for you, but it's not really that hard. They are on Attribute Explorer. So that's another advantage, that the effective switching frequency is twice as much as the real switching frequency. So let me write it down here. Oops. It's twice the switching frequency. Okay. And then, so the mode, this converter, or this particular, the 2 switches that we have, there is an extra mode that we haven't even used at all, and that is when we turn S1 and S2 on together. For the steady state operation, we don't really need that. But there might be a transient situation that you really want to apply a large Vx so that your inductor ramps up really quickly. So in those cases, you can actually detect the transients in the system and turn S1 and S2 on simultaneously for a short period of time so that inductor current ramps up really quickly, twice as much as the regular case. So inductor is small to begin with, then you can expose it to Vin, which is twice as much as a effective value of the buck converter, so your ramp value is going to be really, really large. There are so many good things about this topology. Now, let's move on. I'm kind of trying to segue into a kind of a new class of converters that we are not really cover a lot, which is switch capacitor converters. But we may want to discuss them just a little bit here. So let me read about this topology. Okay, so let's do it like this. Oops, we don't have a source. Oh. Okay. S2 prime, S1 prime, okay. Okay, now I'm going to introduce another switching scheme, and the switching scheme is like this. Let's say our objective is to have an output voltage that is Vin over 2 actually, okay? So our objective is V out should be Vin over 2. So going back to this duty cycle, we realize that for the output voltage to be half of the input voltage, the duty cycle should be 100%, okay? What does that mean? That means your switching pattern is like this. So first you turn S1 and S3 on, or S1 and S2 prime basically. Okay, let's say S1 is on, S2 is off. And obviously the complementary switches can take care of themselves. And this is Vx. So this level would be Vn minus Vn over 2. Okay? And then for the second half of your period, you just turn S2 on and S1 off. This gives you again Vn over 2, which is Vc. Okay. And the average value of Vx is the output voltage. Therefore, your output voltage is Vn over 2. Okay? So you can argue that Vx is almost, at any given time, Vn over 2, right? So let me write it like this. V out is the average value of Vx. Therefore, it is Vn over 2 if we neglect the ripple on the voltage of the capacitor, okay? So technically you can say Vx is almost Vn over 2. Remember, this only is true if we want the output voltage to be half of the input voltage. So remember, Vx is the voltage on the left terminal of the inductor with respect to the ground. V out is the voltage on the right terminal of the inductor with respect to the ground. So if Vx and V out are almost the same, that means the capacitor doesn't see any voltage drop on it, so we can just eliminate the inductor does not see any voltage drop across its terminals, so we can just eliminate the inductor. Okay, so let's do that. So no need to have an inductor. So let me write it this way. VL is almost 0, so no need to have an inductor.
Then we ignore the ripple, right?
Right. No need to have an inductor. So this is assuming that the capacitor, that flying capacitor, is large enough, so the ripple is small. And technically, Vx would not really look like that. There's a bit of a ripple on Vx as well. So that's why I'm writing here, it is approximately equal to V out. All right, so what happens is, so if you eliminate the inductor, all right, let me draw the switches first. Okay, something like this. So first of all, what is the advantage of eliminating the inductor? There are several advantages. Inductors happen to be the bulkiest components in the system. There is always hard to deal with, magnetic materials. They are relatively expensive. There's current passing through this inductor, so we eliminate the inductor. Actually, there's going to be a little bit losses that are going to be eliminated. And these type of topologies are called switched capacitor converters because we only have switches in them and capacitors. There's no inductors in them. All right. So following the same switching pattern, so technically what happens is, let me draw the switching patterns. So this is Vn. We have S1 on. Then this capacitor, the flying cap is is engaged. Then S2 is off, therefore S2 prime is on. So this is like mode 1. All right, so technically we are really not violating KVL at all. Remember, all these capacitors are considered large capacitors, so they are stiff voltages. So this is Vn over 2 plus another Vn over 2, which gives us Vn. Okay, KVL is not violated, assuming that the capacitor voltages are exactly at Vn over 2, but they are slightly higher and lower. So in that case, KVL will be violated. And don't worry about that because these capacitors all have internal resistances. So there's a bit of a resistance here. There's a little bit of a resistance in the source. So the difference between the voltage of these capacitors and the source is going to appear on these little loop inductances, or basically loop impedances or resistances. So what happens is we are going to have a spike of current and then nothing. So this spike of current happens because the voltages are a little bit different from each other. So the source is probably pretty much trying to charge this capacitor as well as providing charge to the output, basically. So if you have an impulse of current, then nothing going on until you jump to the second mode. And in the second mode, what happens is the source is disengaged, basically. And it is the capacitor that is connected over here. All right, something like this. So this is mode 2. So again, this cap is Vn over 2. The output voltage is Vn over 2 too. So KVL is almost not violated unless there is a little bit of a ripple in these voltages and they are slightly different from each other. And no problem, because then there is a little bit of an internal resistance here that takes care of that. So again, you will have an impulse of current It's like the capacitor, the flying capacitor, which was being charged previously, now it's being discharged and delivering power to the load. And that is one of the disadvantages of this converter. Your currents are very pulsating kind of a current. They are not continuous like an inductor current kind of a thing, because you eliminated the inductor basically, okay? So this is a very classic, simple switch capacitor converter. And then you can argue that you can do almost the same thing if you swap the place of your input and output. So here our gain was 0.5 basically, a constant of 0.5. But then you can also swap the place of your input and output voltages and have a gain of 2, like a boost converter, or a boost converter without an inductor basically. Switch capacitor converters have been around for quite some time. Advantages, disadvantages. Advantages, they don't have inductors. So especially when it comes to, for instance, miniaturization of power electronic converter, like at chip level. In your chip, inside your chip, you need a DC-DC converter. Making inductors in a chip is really difficult. You need a lot of area. Making capacitors is not as difficult. Still, you need some area. And making switches and transistors is very easy. So preferably, you want to avoid inductors in a chip. So there you go. You have a topology that doesn't need any inductors and it still does DC to DC conversion. The disadvantage is your output voltage is not really regulated. It's just half of your input, basically. You can't really say, my input is 5 volts. I want to have a 3 volt output. It's only 2.5, okay? So there are some limitations there as well. So any questions? All right, so I'm going to write some of the advantages and disadvantages here. So let's call it inductorless DC-DC converter. Okay, so one advantage is no inductor. So you have a high power density. Okay. One disadvantage is the voltage transfer ratio is fixed. It's just 0.5 in this particular topology. Okay. All right. Also, another disadvantage that we didn't talk really much here is your voltage transfer ratio kind of depends on the internal resistance of this capacitor. So if you really do some modeling over here, you're going to realize these internal resistances that I drew in red would have an influence on your, in a particular switching frequency range, they have an influence on the voltage transfer ratio. So that's a disadvantage. Voltage transfer ratio, it depends on the internal resistance of the components. And if you even want to further generalize it, not just the internal resistance, just the impedance of the loops, basically, because there might be some parasitic inductance there too. The other problem is the ripple. Your current has a ripple, therefore your voltage also has a ripple, the voltage of the caps also, so high output voltage ripple. Okay, because remember the inductor is basically a filter there. It's making a second order filter and we are reducing that order to the first order filter. One advantage is that bidirectional power transfer is easy. Okay, so what do I mean by that? Pretend you have a bidirectional buck topology, right? And this buck converter is, for instance, transferring power from a high voltage battery to a low voltage battery, for instance, in a hybrid vehicle. If you decide to change the direction of your power flow, let's say previously you were operating like this, For instance, the vehicle was accelerating, then all of a sudden the driver puts on brakes and you want to send energy back or something like this. So you want to go to a negative value for your inductor current. But remember, inductors have limitations, a slope limitation, so it's going to be like this. So it's going to take some while to actually reverse the polarity of power, because it takes a while to reverse the direction of the current of your inductor. Over here, there is no inductor, so we don't actually have this limitation. As soon as we change the, basically we modify the switching pattern, you can actually start getting power from your right load or whatever it is and send it to your source, basically. So no delay, basically. Okay. Any questions? So this opens up the whole category of switch capacitor converters. There are many topologies. This was just an example. You can get several PhDs just focusing on basically switch capacitor converters, optimizing their performance. Dr. Kimball has done some research on it. Like he had one of his students, I think it was Lucas, I believe. He was working on these, modeling these topologies basically.
Excuse me.
Yes.
I have a question. Can we eliminate having a compensator for this topology because there is no inductor?
The compensation, yes, actually, as a matter of fact, when it comes to controlling this, you don't really need a compensation network. You don't even need a okay, I shouldn't say you don't need a feedback loop, but I mean, it naturally gives you an output voltage which is half of the input voltage, ideally. So basically, you don't really need to worry about if my output voltage is regulated or not. You can just run it in an open loop fashion and still get an output voltage which is half of your input. So, but it's not very well regulated because of the parasitic components and stuff like that. But yeah, you can do that. You can run it as an open loop, basically, like a fixed 50% duty cycle. Any other questions? One of the papers that I came across using this topology, other than like low power chip applications, integrated circuit application, is for a basically in a vehicle, in an automotive system. Conventional vehicles run on 12-volt batteries, but then there is this pseudo 48-volt system or something like that to raise the voltage level of even conventional batteries for high power applications. For instance, you have a very high power stereo in your car, I don't know, 1 kilowatts or whatever, I don't know what is considered high power in a stereo. And your 12-volt system cannot handle that. Or you have a suspension system, an electromagnetic suspension system, which consumes a huge amount of energy in a short period of time once you hit a bump, something like that on the road. So in those applications, you can argue that if we had a 36-volt battery in the system in our vehicle, then the losses would be smaller than just having everything based on 12. Because if you are draining a huge amount of current from a huge amount of power from a 12-volt system, then the current is too much, and the RS, the conduction losses are going to be too large. So one application that I've seen in a paper is actually using this topology for this exact application. So you have a source or sometimes a load, which in our case is our basically 36 volt, the 36 volt side of the system. Like, I don't know, an active electromagnetic suspension system. Sometimes it consumes power, sometimes it generates power. And on the other hand, you have the conventional 12-volt system. No, yeah. And then again, there are a bunch of loads and sources connected to this 12-volt system. So loads are the conventional loads in a vehicle. A source could be like the alternator or something like this. And then you have these kind of switch capacitor topology going on here. All right. So we said one of the disadvantages of this topologies was that the voltage transfer ratio was fixed. Another problem here, because here we are dealing with two batteries and they have relatively constant voltages anyway, so we don't have to worry about it. So this part is the conventional vehicle. And the one on the left is like the pseudo 36-volt system, basically. And then the switching pattern is, for instance, you turn, the switches on and off in a way that you're converting 36. Let me write actually the switching pattern. It's 1, 2, 3. Okay, S1 on. S2, S5 is on, S2 is on, S2 is off, and S3 is off. Okay. And then you have a system like this. I'm afraid, okay. I'm not going to draw the polarity of these caps because I may miss something. So I'm just going to assume they're non-electrolytic caps. Because you have a system like, so you're not violating KVL. All you're doing is like pretty much you're charging both the 12 volt and 24 volt capacitors. And then you turn S2 is on. S1 is off, and then S3 is also off. And what happens is you have this 12-volt capacitor that is charging, the 24-volt capacitor that is charging your the other capacitor, as well as providing power to the load. And then ultimately you have S3 on, but S1 and S2 are off. So in this case, you have the last capacitor placed with the output side. Okay. So the smallest capacitance in terms of voltage rating is getting discharged and providing power to the load. So I've seen there are applications for this for automotive, and remember, reducing an inductor from a vehicle is actually a good thing because it's a portable application. So if you can get rid of a bulky, half a pound or even a pound of inductance, that would be a reasonable thing to go after. All right, any questions? So this kind of wraps up our discussion on multi-level power electronic converters. It's a very active research area. We have a lot of researchers working on this, trying to make these converters more efficient, try to come up with some redundancy or take advantage of redundancy in a better way, or controlling them in a more effective way. Achieving higher voltages, uncharted territories for power electronics like 20,000 volts, 30,000 volts, those kind of places. Then we are going to step into a new class of power converters, which are called the matrix converters. So we are moving on to a new kind of trying to introduce a new class. Now, matrix converters are not very common, and we are not going to spend a lot of time on those, but I thought it's not a bad idea to introduce them so that in the future, when you see somebody talking about the matrix converter, you can actually understand what they're talking about. There are other names for these type of converters. As it turns out, all converters that we have studied so far are a special case of matrix converters, basically. So other names for these the matrix converter is called cycloconverters. Like back in the 60s and 70s, they were called cycloconverters. Sometimes they are called direct frequency converters. And we are going to see why they are called direct frequency converter, but in a nutshell, if you want to convert one form of AC to another form with a different frequency, you don't have to rectify it into DC and invert it back. You can directly do that. And there's another name for that which sounds like it's Italian. I don't know how to pronounce it, like Venturini or Venturini converters. Okay. What is the functionality of these converters? Are these DC to DC converters or DC to AC? Actually, they can do everything. So technically, you can use one matrix converter to do all the jobs for you, and we are going to see how. So they do all sorts of jobs. So for instance, they can rectify AC to DC. They can convert DC to DC. And they can invert DC to AC. All right. What are the applications? Usually we use them in high power application. That's why we usually don't see them, because high power, I mean multi-megawatts of power. The reason is they have so many switches in them, so they may not be very cost effective in low power applications. Okay, and by the way, I forgot to write direct AC to AC here too. Okay. All right. So as I said a few minutes ago, all converters that we have seen so far are a special case of a particular matrix converter. So let's take a look at this. For instance, when you study power electronics, one of the first things that they introduce to you is this bridge rectifier. Okay, so this is the simplest matrix converter possible. So we have an input voltage which is AC, and we have an output voltage which is kind of rectified. It's not really DC, but it doesn't have any negative portion. So if this is our input voltage, our output voltage is like this. So it has a significant DC component in addition to twice the line frequency ripple. Now the question is, do we like this ripple or not? Do we care about this ripple or not? If we actually would like to have a very clean DC signal, then you have to filter this, capacitors and inductors and things like that. All right. You have seen this before. Very simple bridge rectifier. I'm just going to draw this a little bit differently to get to my matrix kind of converter point. So I have two lines on the input side. I only have one source, and it has two terminals. And I also have two lines on the output side because it's like a single phase kind of an application. Okay, so I have like a network, a mesh, a matrix of basically wires, something like this, and then I am placing the diodes over here. All right, one is here. The other one is here. The other one is here. And finally, this one is here. So these two topologies are basically the same. I've just drawn them differently so that I would form my very basic 2x2 matrix converter. So this is a 2x2 matrix converter. All right. Why is it called 2x2? Because I have two lines on the input side and I have two lines on the output side. Okay. Now, as soon as we see this, we can easily generalize it. We can actually form, I don't know, m by n, basically, matrix converter. So let me draw that one, generalize this. So let's say I have a bunch of lines here, like VI1, VI2. These are all input voltages, stiff input sources. VI3. And I don't know, I'm sorry, I said 3, but I drew 4. And VI4. And you can actually add to these lines. A lot of times our source is a three-phase, maybe a neutral point as well. So maybe a maximum of 4. I don't know. If you have a 6-phase or a 5-phase system, you may have more. And then technically you have I don't know, switches that have so many throws but only one pole. To select between these lines. And we have several of these lines on the output depending on your load. Is it a 3-phase load, single-phase load, I don't know, 5-phase load, whatever it is. So like this is your second line on the output side. Let's just draw a third one too, pretending it's a 3-phase system. All right, something like this. Okay. And then you can actually have more down here. Okay. All right. So in general, we have M input voltages. They're all stiff. Like for instance, a three-phase source, voltage source. And then on the output, I have n outputs. And they are all stiff currents. Okay? So you're going to come up with a name with this topology. It would be an M by N voltage-fed matrix converter.
Dr. Ferdowsi?
Yes.
When we say stiff current, does it mean that the polarity of the current is fixed?
No. Stiff means it's like an inductor on the path of this current. So this I out 1 does not, well, necessarily, I mean, it depends on the application. Necessarily, it doesn't have to be a stiff current, but most of the times there is an inductor over there. Like if you're if you're trying to provide power to an electric motor or something like that. So there is an inductor there. That means I out 1 and I out 2 and I out 3 do not suddenly change from a number to the other because they are continuous currents basically. What about the switches? Remember, whenever we draw a switch, we have to worry about the realization of the switch. So if you actually look at these switches, these guys are, there is a single pole here, but we have M throws. And we have n of them, okay, whatever the number n is. In general, you can argue that depending on your switch realization, the power flow should be bidirectional. There is no restriction there as long as you consider that in your switch realization. This doesn't look a lot like a matrix, but I'm going to redraw this again, and I'm going to make sure that it looks like a matrix. It somehow looks like a matrix anyway, but let me just redraw this. And you add bunch of switches over here. This is kind of like a switch realization. How do we realize that single pole M throw switch? And this diagram looks more like a matrix kind of a thing. So you still have VI1, VI2, VI3, and VI4, and then you have I out 1, I out 2, and 3. Okay, and obviously you can extend to the number of your inputs or add to the number of your outputs. So you have N poles here and M throws here. Okay, now remember these switches over here, these M single pole, single throw switches that I have here, collectively they form a single pole M throw switch. Okay, which is equivalent to M single pole, single throw switches. Okay. So remember, so the reason that I'm actually highlighting this issue is at any given time, only one of these switches and only one of them should be on. Like here I have 4 switches. At any given time, like if this switch is on, the other 3 should be off. Or when we have this switch is on, the other 3 should be off. Otherwise, you are violating KVL, because if I have this switch on and this switch on, I'm kind of shorting these two stiff voltages to each other, and KVL is going to be unhappy. So just make sure that you have that in mind. All right. What about switch realization?
I have a question.
Yes.
Will there be a case where neither of those 4 switches is on?
There might be a case, depending on the application, if you are looking at like a discontinuous conduction mode for I-out1, like I-out1 reaches 0 and remains at 0, that means all of those switches could be off potentially. But assuming that this current is almost 99 or all the time non-zero, that means at least one of the switches should be on to provide that path of conduction. Any other questions? Okay, so in terms of switch realization, we can go with the very, let me redraw this. Very general case of a 4-quadrant single pole, single throw switch. All right. Okay. This is the most general case possible. It can accommodate positive currents or negative currents, no problem. It can accommodate positive voltages and negative voltages. Positive and negative voltages are in a sense that we don't know if Vi1 is larger than Vi2 or not. Or they could be AC signals. So sometimes Vi1 might be larger than Vi2, and sometimes it could be smaller than Vi2. I mean, if it is an AC signal, because we don't know anything about them, we go after the most general case. Or if you remember switch realization from before, we can do the same thing. You can get the same functionality out of putting 2 of these basically IGBTs with anti-parallel diodes in series with each other. All right, something like that. So this does the same thing. The only disadvantage is now you're using 2 switches rather than only 1 transistor. Okay. Although the switch realization might be simpler depending on the application, for instance, in this very simple rectifier example that we had, the output current was always in one direction, so we don't have to worry about bidirectional current. I know you only have 2 lines, and I kind of know that sometimes one line is larger than the other and sometimes it's not. So my switch realization was reduced to only 1 diode per switch basically, and 4 diodes because I need 4 switches. Okay, any questions so far? Yes?
In which specific case do we have a realization of the kind of switch that we just drew?
Like this one?
Yeah.
Like these guys?
Yeah.
So the question is, in what cases do we actually realize the switch like this? In cases that you have either no information about what's going on in the system in terms of power flow, or you have simulated the system and have come to the conclusion that it's an AC to AC kind of a signal. I-1 could be positive or negative, and VI1 and VI2 are also AC signals. So you actually realize the switch is like this. All right. Okay. So as I said earlier, one of the names for this topology is actually direct frequency converter, and we are going to see why right now. So technically, a lot of times when you have an AC source, let's call it's a single phase AC or I don't know, 3-phase AC source. Okay. And we are trying to drive an electric motor, but at the same time we want to control the speed of that electric motor. So if you go back to the discussion about controlling the speed of an electric motor, one way is to control the frequency of the AC signal that is applied to the electric motor. Now, unfortunately, our source is fixed frequency, so we can't really change the frequency. So what you got to do is you got to rectify this to DC. And usually power factor correction is important to you, and we are going to actually discuss power factor correctors soon, probably next week. So technically you end up with a DC link. And then you got to have an inverter. To provide power to your electric motor, assuming that it's a 3-phase motor. My drawing is based on that assumption. So this could be single or 3-phase. Okay. So as you can see, so here we have a variable frequency basically. Or maybe variable amplitude, or maybe both. Okay, and you have some sort of an energy storage here. It's not storing a humongous amount of energy. It's like more like a filter, basically, like a buffer for energy. And this approach is called indirect frequency conversion. The reason that it is called indirect is because it's not direct. And why is it not called direct? Because we haven't talked about direct yet. And basically what you do is you convert your entire power from AC to DC, and then you invert it back from DC to AC. The next approach, we could actually use a matrix converter to do this, is just to eliminate all these converters and power converters, and just put a matrix converter here. It usually works when you have a 3-phase source, though. All right, and this is what we are going to see basically next time. So the handouts that you guys have right now is bring them with you on Thursday, and if you are a distance student, actually going to put these handouts as a PDF file on Blackboard, so you don't have to do all the drawings by yourself. Okay, see you guys on Thursday.